Assalamualaikum dan selamat sejahtera. Now, subtopic 7.3, Solubility Equilibria. Okay, first of all, you have to know the terms that normally we use in this subtopic. The first one is solubility. What means by solubility? Is the maximum amount solid in unit gram or mole or kilogram that can be dissolved in a given quantity of solvent to form saturated solution at given temperature. So, the unit of solubility normally used in gram per liter. Sometimes, the solubility also can be in unit mole per liter. Okay, what means by solubility? Gram of solute dissolved in 1 liter of saturated solution. How about molar solubility? The unit is mole per liter. Moles of solute dissolved in 1 liter of saturated solution. Here, the unit for molar solubility always in unit mole per liter. But unit for solubility sometimes in gram per liter, sometimes in mole per liter. Depends on the data given. But these two terms is to form saturated solution. So what means by saturated solution? The solution that have in equilibrium between solid phase and aqueous phase. So, di situ kita akan nampak satu solution yang ada solid dan ada aqueous pada masa yang sama. That means by saturated solution. Okay. Then, you have to know what is solubility product constant. The symbol is KSP. Okay. From the previous lesson, we already learned about Ka, Kb. For chapter 6, Kc, Kp, right? But for 7.3, you learn about Ksp, solubility product constant. Okay. For example, you have saturated solution silver chloride in water. So, this silver chloride here is a salt that partially dissociate. Okay. Produce Ag plus and Cl minus. From this equation, we can write its Kxp expression. Okay, how? Okay, as usual, Ksp only consider the phase of aqueous only, right? So, as usual, concentration product, which is Ag plus, power is Tokyo 1, multiply concentration Cl minus, power is Tokyo over concentration reactant. But for this, your reactant in solid form, that's why we no need to write in Ksp expression. So this is we call as Ksp expression. Now we go to the next term. Okay, you want to recognize about the ionic compound that we use in solubility equilibria. Okay, the first type of ionic compound is we call as slightly soluble ionic compound. Okay, in this subtopic, normally we use the salt we call as ionic compounds, right? When ionic compounds is lightly soluble but 100% dissociate in water produced such as PbCl2. Okay, let's say this is your ionic compound. This ionic compound is only slightly soluble. But it does not mean that it does not dissociate 100%. It still dissociate 100% to produce its ion, which is anion and cation. Right? So, based on this ionic compound, which is slightly soluble, it must have the Ksp value. But the Ksp value for this slightly soluble ionic compound is very, very small. The second type ionic compound is soluble ionic compound. This ionic compound very, very soluble. That means 100% soluble in water, and also 100% dissociate in water. For example, NaCl here. Okay, this salt is very soluble, and it also dissociate 100% to its ion. Alright, so but it doesn't have Ksv value. If it have Ksv value, the Ksv is very, very large. Okay, normally it does not have Ksv value. So here we can't use reversible arrow because it's very, very soluble ionic compound. Thus, we must use the single arrow here. So remember, these two ionic compounds still 100% dissociate to produce its ion, but the difference between these is a very slightly soluble. It is very 100% soluble, very, very soluble. Now we go to the exercise number 1. We want to try to write the ion product expression, or we call as solidity product constant expression for each of the following ionic compound. Okay, so for A, silver carbonate. First of all, you have to determine the molecular formula for silver carbonate. We know silver is Ag plus, carbonate CO3 2 minus. You have to cross the charge to get the molecular formula of the ionic compound, which is Ag2CO3. So all the ionic compound in phase solid, okay, use the reversible arrow because all the ionic compound given is slightly soluble. So it 100% dissociate into its ion Ag plus and carbonate. All the phase of ion is aqueous, and then you have to balance. So from this equation, you must write the expression: concentration product, power is Tokyo, concentration another product, power is Tokyo, over the reactant. Since your reactant in solid, no need to write. So this is your Ksp expression. Now for B, barium is 2 plus, fluoride F minus, cross the charge, you will get the molecular formula for barium fluoride. Okay, reversible arrow, Ba2 plus aqueous and F minus aqueous. Balance the charge, balance the stoichiometry, then you write the expression. Power is Tokyo, power is Tokyo. This is your answer. Copper 2 sulfide, that means copper 2 plus. 2 Roman here, that means 2 plus here. Okay, sulfide S2 minus cross the charge, you'll get the molecular formula. Alright, then produce it, ion. Okay, balance the stoichiometry and write the expression. Power is stoichio, power is stoichio. This is your expression. D is iron 3. That means Fe3 plus hydroxide OH minus cross the charge, you get Fe hydroxide. First solid. Okay, produce its ion. Okay, balance the equation 3 here. So you get SP expression is power is stoichio, multiply another product, power is stoichio. Okay, next for barium phosphate, Ba2 plus, phosphate PO4 3 minus. Okay, cross the charge, you'll get the molecular formula. Right, the phase is solid, produce its ion. Cross the charge, 3 here, 2 here. Okay, SP expression, concentration barium, power is stoichio, concentration phosphate, power is stoichio. 2 here. This is your SP expression. The last one, tin 2 sulfide, tin 2. That means SN2 plus sulfide S2 minus cross the charge, you will get SNS solid, produce its ion. Right, balance the charge, the stoichio, write the SP expression. Settle for your exercise number 1. Okay, now I want to show you using KSP you can compare the solubility. That means based on the value of KSP you can determine which one the ionic compound is more soluble. Alright, but with one condition, the formula or the ionic compounds must have same total number of ion. Like this, okay, MgCO3 and PbSO4. Same total number ions. Here that means your cation is 1 compared to Pb2 plus also 1. How about the anion is also 1 mole. How about SO4 2 minus also 1 mole. So since the cation and anion is similar number of mole, yes, you can compare the solubility between these two ionic compound. Okay, so from these two value 3.5 and 1.6, when the value of KSP becomes greater, becomes higher, the solubility of the ionic compound also increase, because when the KSP value is increased, okay, that means the concentration of your product, okay, is also increased. This concentration of your product is come from the dissociation. Come from the dissociation of ionic compound. Alright, So more dissociate of ionic compound, more concentration product produced. So the KSP value also increase. That's why between these two, MgCO3 is higher solubility compared to PbSO4. Okay, this concentration product means that concentration of your cation and anion. Right. So next, we want to calculate the KSP and also the molar solubility. Before we try to calculate KSP or molar solubility, you have to remind one note. Okay, if you want to calculate KSP, no need to use ice table. The second one, if you want to calculate molar solubility, yes, compulsory, you needed ice table.